Still on the investigation of the motion of particles, or subatomic dimension, it behoves us to specify the characteristic nature of the particles as they traverse dimensions under investigation. Hence, particles in the microscopic dimension are seen to exhibit some particle and wave property. Hence, the wave-particle duality. The fundamental question that triggers wave-particle duality reason is that given a particle of, say, as n, moving in free space, the velocity v sub x, or linear momentum p sub x, which is the same as the product of mass velocity. What could be the possible state function of that particle? That is, this particle is moving freely. So the idea now is what be possible state function of state function here. So by reasoning in line, the postulates the state function must be the eigenfunction corresponding to the eigenvalue. The state function in this case, this particle is moving to momentum p sub x, then the state function must be the eigenfunction psi p of x psi sub x. So to describe this entire process, then we need to describe psi sub x in relation to the momentum. So state function must be the eigenfunction corresponding to the eigenvalue p sub x, which can be of a positive or negative value, okay, depending on the direction. The operator p sub x represents the x component, the linear momentum, okay? So, hence, this is the same as p sub x. So, now, if we have this put in place, then from postulate 2, corollary 2, we have that p sub x hat is the same as minus j h cross x. And p hat sub y, same as minus j h cross y. Then p sub z hat is the same as j h cross d. So the above expansion reduces to a simple ordinary differential equation. So since the operator is complex, it's the same as this. So this entire expression, therefore, written as j j h cross dx sub sorry, the same as what And then, just like shown before, solution to this differential equation, so it's first, the same, say C be the constant, epsilon J E sub X H cross. Where C is a constant to be determined by the normalization constant, by the normalization condition. So C is a constant, right? Okay. Since the particle is in free space, it's already established now, like this reason, okay? It's in free space. Meaning there is no boundary condition on the state function because it is expected to move freely. Now, should this particle be incident upon a boundary, probably of different layer, then we begin to establish some boundary conditions at this point. Okay? But in the case of free space, particle is assumed to freely. Hence, there are no boundary conditions in the state function. Also, the velocity or momentum of the particle can have any value and is a continuous eigenvalue of the operator P of the momentum operator. Hence, the probability density function PDF density function, which is a mod squared of the state function be the same as square root of C. Note that the PDF is a constant independent of X because the constant is independent of X. Hence, this implies that the particle will be anywhere since it is independent of the position X. Okay? Now, since PDF is a constant, meaning it is independent of X, it implies that particle be anywhere in space. And put differently, according to the Heisenberg's uncertainty principle, if the linear momentum of the particle is known precisely to be of some value, say P of X, or the uncertainty value is to be some precise value, say P sub X, then since it is known, it means that the uncertainty in P sub X is 0 because it is known. It's not uncertain, it's certain, it's known. Therefore, the uncertainty in the position will be infinite. Recall that the position and the momentum don't commute, isn't it? From our previous lecture. Yeah? Since the uncertainty product is the same as h cross over 2, then it means that the more we know the position, the momentum, the less we know about the position. And the more we know about the position, the less we know about the momentum. And since the momentum is known precisely, then it means the uncertainty in the momentum is 0. Then the uncertainty in the position x will be very high. So it must be infinite. And the particle meaning, hence, particle can be anywhere with equal. We cannot really say this is the exact location, this is the exact position. So recall that in quantum mechanics, a particle traveling with a constant velocity, v sub s, always means an ensemble of similarly prepared particles all in the same state, having the same linear momentum, v sub x being the same and similarly prepared particle, so can tell its location, its position. Now, if that's what it is, then also recall that the uncertainty principle states that it is fundamentally not possible to specify the position and velocity precisely, simultaneously. And since C can be fixed by the normalization condition, let's consider two scenarios then. So in the first case, let's assume only a single particle. So say case 1, let's say a single particle exists or space from x taking values from negative infinity to positive infinity. Now, since the condition given so far, probability distribution function, is independent of x, that is, it is mod squared of a constant, which is 0, then should there be n particles, should there be n particles per unit length in space, or put differently, there is one particle in the space range n, then what's c squared over n is the same as the integral taken from 0 to 1 by n PDF squared x. Now this implies that c squared n is equal to, therefore PDF is equal to n, such that c is the same as the square root. Therefore, recall that the solution to the state function is given as c epsilon j piece of s over h cross x. Then now the c is from n, so we have n epsilon j so x over h cross as a solution. This state function describes a beam, describes the state function. State function. So this state function describes a beam of n particles by unit length traveling constant velocity v sub x, which is the same as Photon. So x call photons. So for a free space particle, the Hamiltonian for a free space particle, for free space particle. So the Hamiltonian, say, is p squared, which is the same as this is the velocity particle in free space, which is the same as the energy. Its energy is the same as squared 2n squared squared. Now, the corresponding time-independent Schrodinger equation, therefore, will become the Hamiltonian operator operating on the state function x, therefore, minus h cross squared plus 2n squared squared, which is the same as energy times. Now, if this is our first equation, this is our second equation. So if we substitute these parameters, then psi of x is the same as n j j. So cross x, right? Corresponding to the eigenvalue p equals p squared x. In this case, the energy E is same to the same. This property is very important, meaning the energy of the wave function is continuous in free space. Because as we see in the case of quantum wells, now see that the energy in quantum wells or in confinement is discrete, is quantized. But in free space, it is observed based on this relationship that the energy is continuous in free space. Hence, the energy of a particle In free space is not quantized since P sub s. Now, since the wave function P sub psi P sub psi sub P sub x of x is an eigenfunction of the Hamiltonian, is an eigenfunction of the Hamiltonian cross, which at the energy and linear momentum of a particle in this state can be known or simultaneously measured precisely. Okay? That is the energy and the linear momentum. That is the Hamiltonian and the linear momentum px of height commute, since they can be specified simultaneously. So quantum bracket, the Hamiltonian and linear momentum is the same as h cross right 2m squared x squared. This is j h cross b x is equal to 0. Observe that its properties show some Note that the knowledge of the eigenfunctions of the Hamiltonian implies that it is possible to find the solution of the corresponding time-dependent Schrodinger equation, or the time dependence of the state function. Okay? Hence, we have that okay, fine with that. Let us compare both. So now already have the solution that x in terms of the position, so square n, so j x minus cross x. Now the time dependent Schrodinger equation, the time dependent Schrodinger equation can now be solved such that psi st is related to x will now be n epsilon j cross x j e h cross t. Note that this equation here has the form of a plane monochromatic wave in which only one frequency component is present. That is, this is of the same form, say, psi c X. So J T. If that is true, then it means that this component is related to number, variation constant. This component is related to angular. So here can specify or variation constant case of X to be the same as the momentum that reduce constant. Then the angular frequency and C may now be same as the energy divided by. Now, since omega is the same as 2 pi f, therefore C is the same as A plus. Okay. Hence, from this property, you know that H cross is the same as the Planck constant divided by 2 pi. So it's that 2 pi f is the same as E of H over 2 pi, such that 2 pi f is the same as 2 pi E H. This for frequency seems to be a function of the energy and the excuse me. Hence, the energy particle seems to be proportional product Planck constant and the frequency, which happens to be the Einstein's also recall that the speed of light is proportional to the wavelength, such that f frequency is now the same as speed of light, the velocity. Therefore, this photon energy, therefore written as substitute for frequency c over lambda. But according to special relativity, we have squared same as b x squared c squared same as c squared. So, and if this parameter is as small that approximate to 0 value, then b so x squared is the same as u c, such that energy is a function so b x is c energy same as the momentum, same speed of light. Now, if we compare this, let's call this separation, equations. If we compare them, so it means that we have E to be the same as HC as C. And hence, to cross the speed of light here, so the momentum is directly related to the Planck constant. So it can be observed that the Einstein's model links particle and wave properties based on the following equations. As derived, then sub x is equal to okay. So observe that the energy and the momentum, linear momentum, particle describes the particle property, while the frequency and the wavelength describes wave property. So the Broglie therefore assumed that these two properties hold for all matter particles, including electrons. So the Broglie proposed that for a matter that for matter, the particle with momentum p sub x, you can associate a plane wave of wavelength lambda d being the same as h by the now, this equation predicts that the de Broglie wavelength of a matter wave is associated with the motion of a material particle with momentum p sub x. And note that the probability density function, as we showed earlier, T is the same as n in the intensity. This is the intensity of the beam. Since the state function links particle and wave, this particle therefore can be regarded as a matter or a Broglie So that the state function can also be called state function. We're talking about state function. Psi can also be called wave function. Because in as much as it can describe the state of the particle, it can also provide information about the wave property. Hence, the de Broglie wavelength lambda d, which is the same as h cross h over this, follows directly from previous analogy, kx, because said k sub x for that. So then, if we have 2 pi e x over h cross from our equation, then we know that 2 pi h cross p sub x will give us 2 pi dot h over 2 pi h over 2 pi divided by p sub x. So cross this h over p sub x, as we have seen here, and also know that linear momentum is related this expression. So should a particle be traveling in a region of constant potential energy, say not in free space, the free space, like I mentioned earlier, so there's a boundary and it's traveling into this region. Okay, so this is the incident, this is transmitted wave, expect a reflected wave instance. Now, this part describes the potential difference, say V, then the de Broglie wavelength other than free space, other than free space, then the de Broglie wavelength h divided square root 2n. The energy wave minus the energy of the wave in this medium minus the potential, the energy of the wave in this region, say V. Hence, the equivalent relative index of refraction of the medium is now equivalent. So is that the relative refractive index is now proportional to E minus V by squared, and can be changed through the potential energy. It can be changed with potential energy term in the Hamiltonian. Okay. So as this varies, this may reduce to 1. So for charged particles such as electrons and ions, electrostatic potentials can be used to manipulate the Broglie. Okay. So now, if, for instance, assume that the linear momentum of a particle is precisely specified such that the uncertainty in the linear momentum is not the same as 0, so meaning we know the value p sub x some level of certainty, right? So your certainty in the linear momentum is not zero. According to the uncertainty principle, the uncertainty in the position of the particle, that is, will not be equal to zero. Okay? Because the more we know one of them, less we know. So they don't connote. That is, the particle cannot be catalyzed. Okay? For the position of the particle to be known precisely, the momentum must be totally uncertain. So, by Heisenberg's uncertainty principle. So, if we decide to know the value of the position, then momentum speed. So this is so hence the position and momentum exhibit some conjugate relationship, right? So this conjugate relationship between the position and the momentum can be expressed as psi of x, which is integral psi where psi of x then the integral psi is conjugate psi sub x psi x x the x is the same as the delta sub x minus x prime. Okay? Now the eigenfunction psi sub x is normalized to satisfy the condition of orthonormality for the continuous eigenvalues. P sub x such that psi e sub x of x is the same as 1 to I cross so g sub x such that integrated conjugate of x psi dx is given as say L 10 to infinity to I equals x minus b minus x, x. Solution same as 1 over I, taking it for L tend to infinity, sine p, so it's minus b L cross, so that's minus, so that's, which is the same as theta squared. And by substitution, that is, if we take this for instance, and then plug it into this expression, okay, that is star to star, it is seen that an arbitrary state function may be expanded as a superposition of the Broglie waves. That is, psi of x sine to cross is equal to infinity to infinity psi exponential j squares. And in a similar vein, if we also this expression, that is star, so it's space here. So if we also star into this two, it is seen that the corresponding complex amplitude function psi p of x is exactly the partial Fourier transform of the state function. It's 1 so I cross to bracket to infinity. So j so cross so sine x. And this is the linear momentum representation. So the momentum representation state by psi of x Schrodinger representation. So note the corresponding x component of the de Broglie wave vector k sub x is the same as the linear momentum divided by square. So the probability distribution function in the momentum space is the square of the momentum representation of the state function, right? So the PDF, which implies that the Probability distribution function is the probability that measurements of the momentum of the particle in this state will take on a value in the range from p sub x to p sub x plus the p sub x. Now, if the normalized probability distribution function in momentum space is a Gaussian function with an average value, say E, the average value, the expectation value, and then the uncertainty, the P, this is the uncertainty, then the probability distribution function x squared is the same as the Gaussian process. 2 pi squared px is the expected value squared by 2 expectation squared uncertainty. So assuming that the reference phase factor is 0, the momentum representation state function becomes Photon 2 pi squared piece of x minus the expectation value squared uncertainty squared. By taking the inverse Fourier transform, corresponding state function surface 4th root of 2 pi beta x squared epsilon x squared 4 x squared j e expected value e h cross x. The normalized probability distribution function will therefore become, that is in the space, squared squared 2 pi squared epsilon squared. So the average value is the average value of 0 and the uncertainty spread given as uncertainty spread h cross. So uncertainty times uncertainty e squared. So from the following, when the expectation p squared is finite, the probability distribution function of the position of the particle, we also have a finite rate. This implies that the particle can be localized as a wave packet. Okay. Also know that the uncertainty product, so that's the same as H cross over 2. Hence, the Gaussian wave packet is minimum certainty. So we'll stop here and continue from here and next class. Do have a